We're recording. And, yeah, okay, sounds good. There. So this is the quotient rule. If f and g are two functions that are both differentiable, then its quotient must be differentiable. So I'll call this capital F of x, which means it's the division of function f of x and function g of x. And the derivative of this whole thing is this wacky formula here. The derivative of the top times the bottom minus the top times the derivative of the bottom over the denominator squared. And yes, you have to memorize this formula. We're not going to give it to you. It's not as hard as you think. In fact, for once, the Leibniz notation might be easier to remember because most of the time people express the Leibniz notation like this, and then there's a cute little saying that I remember learning it this way when I was in high school. Now, it doesn't matter what order you multiply two things. So this one here at the top says derivative of the top times the bottom. But in Leibniz notation, you usually write the thing you're not doing the derivative of first, like it becomes your coefficient. So the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Now, almost nobody forgets that it's the bottom squared or the denominator squared, but oh, it matters. Notice when I say it doesn't matter what order you multiply, it doesn't matter what order you add, it does matter what order you subtract. So you would goof this up and get the wrong sign if you accidentally had the denominator's derivative first instead of the numerator's derivative first. So how do you remember to keep this straight? Here's the way I remember it from high school. I remember it like you're yodeling. Low-de high, high-de low. And I'm not going to actually yodel for you. That would be cultural appropriation of people from the Alps, I guess. Low-de high, high-de low. Low, derivative high, high, derivative low. This stupid little saying. I'm bad at memorizing formulas, so this stupid little saying helped me a lot. All right, let's actually use our new formula. Determine the derivative. So the derivative is the denominator, low, times the derivative of the numerator. Minus, so that's low d high, minus the numerator times the derivative of the denominator, all over the denominator squared. Let me roll that down so you can see both the formula and the application of the formula on the same screen. I'll go back to my my highlighter here, right? This part is right here, right? This part is right here. This part is right here. And this part, is right here. Right? See the logic on how we made that. Denominator times the derivative of the numerator minus numerator times the derivative of the denominator. So that is, okay, let me get rid of all these. There. Now we got to do a lot of algebra here. We are going to do our best to collect like terms anytime we can, so we're going to expand this. So the expansion of this is going to be 5x to the 6 minus 12x to the 4 plus 14x cubed. Now careful, I'm multiplying and distributing a minus at the same time here. So minus 2x to the 6 plus 8x to the 4 minus 14x cubed all over, I can simplify x squared squared to x to the power 4, right? 2 times 2 is 4. All right. I do see some like terms I can collect. In fact, I see the cubes cancel. That's nice. And 5x to the 6 minus 2x to the 6 is 3x to the 6. And negative 12x to the 4 plus 8x to the 4 is 4x to the 4, and it's a minus. And now, why don't I factor out x to the power 4 from the numerator, divide it by the denominator, or cancel it with the denominator, and I get 3x squared minus 4. Now, is that what you would expect this to be? Well, look at the question more carefully. Yeah, it is. The question is actually a cubic. See why it's a cubic? Because I could have actually divided all 3 of these terms by x squared. It would have been actually easier than all the work I just did. In fact, why don't I do that? I have that one second, but okay. We'll simplify first, then we'll use basic rules. So simplifying first, it would look like this. It would look like, so f of x, let me copy the question again. It's x to the 5 minus 4x cubed plus 7x squared. And if you're wondering why I'm crammed way over to the side, it's because this one will take more room. All over x squared. And if I simplify that first before I take the derivative, x to the 5 divided by x squared is x cubed. X to the 3 divided by x squared is 4x. And 7x squared divided by x squared is 7. And hopefully everybody remembers that you are distributing that subtract. Please, please, please don't just go, oh, I can cancel those, and then think that the answer is x to the power 5 minus 4x cubed. It is not. That does not work. Okay? So that's what it is. And clearly, yeah, when I do the derivative of that, that's totally going to be a quadratic. It's going to be 3x squared minus 4, which is what I got. It's like, so then why did we do this great big formula? Boy, that was way easier. Well, because the divides are going to get more complicated than that. Obviously, if you gave me a divide that looked like this, and you said, hey, do the derivative of that, yeah, this is the way I'm going to do it. This is the tool I'm reaching for in my toolbox. But as you give me more and more complicated rational expressions to try to find derivatives of, I'm going to lean more and more towards using the quotient law to do it. Right? It's kind of like, remember in grade 11, you learned quadratics. If somebody gives you a quadratic equation to solve and it's factorable, if you notice right away you can factor it, don't you just factor it? You don't break out the quadratic formula for everything. That's a lot of work when you could have just factored it. So it's the same idea here. Right? I have to learn how to do the quotient law. So I'm giving you some examples where we're just always using the quotient law. But out in the field, in the real world, I use whatever tool gets me the answer the most efficiently. And certainly on this question, my basic rules are going to do it. And, you know, I could have also used the product law. Or, sorry, rule. I keep saying law. Product rule. The product rule would be to turn f of x, and by f of x I mean capital F, into a product. So it would be x to the 5 minus 4x cubed plus 7x, and then I could have turned the denominator into that. Right? And now, okay, so what was the product law again? Product law order doesn't really matter. So derivative of the first thing times the second thing plus the derivative of the second thing times the first thing. And now here I am again with that dilemma of where do you want to go with that? Do you want to change those to radicals to reciprocals right now and maybe look at them as a couple of rational expressions here and here? I think not. I think this time I'll actually expand that. So let's expand. Expanding. So that's going to be 5x to the 4 times x to the negative 2, which is 5x squared, right? Because remember, I add the exponents. So minus 12, and think about it, x to the negative 2, or sorry, x to the 2 times x to the negative 2 is x to the 0. What's x to the 0? 1, so that's just 12 times 1. And then plus 7x to the negative 2. Meanwhile, over here, I'd have plus, oh, wait a minute. Hang on, something's wrong here. What did I do wrong? Yes, there we go. The 7x is supposed to be squared in the beginning, isn't it? So that actually made this. See, you copy the question wrong and something's going. See, I could tell right away this was going wrong. You copy the question wrong and then you goof it up. So, still goofing it up. That should be 14x, shouldn't it? Yep, right? Derivative of 7x squared is 14x. Thank you. Good eye. So let's see. I did that multiply wrong then because I had the wrong number there. 14x times x to the negative 2 is 14x to the negative 1. There. Now over on this side, negative 2, I might as well not make that a plus. I might as well make that a negative. Negative 2. X to the negative 3 times x to the 5 is x to the 2. And negative 2 times negative 4 is plus 8. But x to the negative 3 times x to the 3 is, again, x to the 0. So there you go. That's just an 8. And then negative 2 times 7x is negative 14. And then x to the negative 3 times x is x to the... oh, hang on a sec. Again, I copied that wrong. This was supposed to be a squared. So negative 3 plus 2 is negative 1. Come on, pen. Hang on. I've confused my pen. There we go. And I'm really glad I did it this way. If I'd have changed these to rational expressions first, then I would have had to have dealt with a common denominator and all that, when look what's happening. The negative exponents end up going away. So I'm going to end up with 5x squared minus 2x squared, which is 3x squared, and minus 12 plus 8, which is minus 4. I don't know that I even need to bother with Desmos on this one. It worked out so nice. I'm pretty sure all three of those answers are the same because they look identical. And it's what I expected. As soon as I looked at this thing kind of critically, it looked really complicated. But at the end of the day, I could tell, oh yeah, that's just a cubic. It's just an x cubed. And when you do the derivative of an x cubed, you know you're getting an x squared. Let's look at Desmos anyway. Come on, Desmos. There it is. Okay, so there it is. Go away. There's the original cubic, right? And okay, so now I've had a few people over the last few days ask me, can you go over that graphing stuff again? So yeah, here's the graphing, right? This right here, can you see where I'm pointing with my cursor? That's where the slope's 0. So right underneath that, I know I'm going to have a 0 right about here. Until I get to that 0, from the left of that 0, everything's positive. So I'm definitely doing that, right? Because everything after this 0 is negative. So I'm doing that. And let's see if I'm right about that. Yep, it is a quadratic. And that was my answer. Oops. Oh. That was my answer. Does that agree with what Desmos would calculate? Can you tell that? It's green, it's blue, it's green, it's blue. Okay. I'm probably going to get through one more, and then we'll have to save the rest till tomorrow. But they're not going to take that long tomorrow. Then you'll get some work time. So here we go. Example 2, or B. Our fancy new rule. The derivative is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. Or as I like to say, low-de high, high-de low. Over the denominator squared. All right, let's expand that. I'm foiling here, so I got to do first times first, so that's 2x cubed. Outside times outside is 2x squared. Inside times inside is 6x, and last times last is 6. This confused people. I remember last year somebody saying, how come when you did a binomial times a binomial, or they actually asked, how come when you foiled, you ended up with 4 things instead of 3? They're so used to grade 10. And can anybody explain that? How come this doesn't simplify to 3 things? What is it about these 2 binomials that meant you didn't get a trinomial when you multiplied it? Because everything in grade 10 turned out to be binomial, right? What do you think?
Yeah,
Exactly. The two binomials had a different degree in them. So that means that if they don't have the same degree, that means you don't get something simplifiable. You get 4 terms. Okay, so make sure that makes sense to you. This guy here, I'm going to try to do 2 steps at once. So I'm timesing by 2x and I'm distributing a negative. So minus 2x cubed. That would be then minus 4x squared and plus 2x. And that is going to turn out to be, oh, don't forget the denominator. It doesn't go anywhere. That's going to turn out to be, those guys cancel, bye-bye. 2x squared minus 4x squared is negative 2x squared. And then 6x plus 2x is plus 8x. And then plus 6. Got a nice, easy to work with trinomial on the top. And this thing on the bottom. Now, oh, wait a minute. There's a squared in here. Yeah. Thank you. I lost my squared. There you go. Now, I get people to say, well, why didn't you multiply at the bottom? And the answer to that question is, there's no, why? What would I gain from that? There's no point. Right? I can tell right away that this thing wouldn't divide into the top. So it wouldn't get it any simpler. So I like this as an answer. And again, I checked it on Desmos. And so let's see. Here's the second question. That's what that looks like. It's an x squared divided by an x squared. People, I asked last year, it's like, well, won't it be a constant? Because x squared divided by x squared is 1. Well, no, it won't, because this denominator doesn't evenly go into that numerator. So that's why you get this funky curve. So now look at this curve. Try to picture what it's going to look like when we derive it. What is everything doing here? All of these slopes are what? What kind of slopes are they? They're all negative, so they're all down here. And they're not very steep, so they're not down here very far, right? These are pretty flat. And then, of course, you get to a 0 here, so I'm going to cross the x-axis. So I'm down here, and I cross the x-axis there. Then all my slopes are positive. They kind of go up a little, right? Because this part here is fairly steep. So it might go up a little and then flatten out, because this part's very not steep. Can you picture that? Let's see if we're right. Yep, that's what it looks like. And then, that was my answer. Does Desmos agree with my answer? It does. It's black, it's blue, it's black, it's blue. We got the same derivative, me and Desmos, aren't we? Good. And there we go. So we'll do like 3 more of those examples tomorrow, then you can have some work time. I'll share this file with you. It's on my blog. And if anybody wants to see the first couple examples again, I'm making a video, which I'll stop right now.